basic principles involved in supplying an internal combustion engine with the right amount of fuel and air haven't changed. However, cleaning up the engine exhaust by ensuring more complete combustion has brought about some changes in carburation requirements. As carburation requirements become more complex, carburetor adjustment and service become more critical. So it's about time we reviewed the fundamentals of carburation as they apply to our cleaner burning engines. Now that I've introduced the subject, I want to introduce a carburation expert, Pete Sampson.
Don't go away, Tech. I may need some help from you in a few spots. The carburetor must supply the engine with the correct mixture of fuel and air to ensure good combustion. And mixture requirements vary with changes in temperature, engine speed, and load on the engine. For example, let's consider temperature. For ease of starting, particularly in cold weather, a very rich mixture is needed. As soon as the engine starts, the ratio of fuel to air must be reduced to prevent flooding and stalling. As the engine warms up, fuel vaporization improves and even leaner mixtures are called for. Engine speed and power requirements also affect mixture requirements. At idle and low speeds, a relatively lean mixture is required to minimize exhaust emissions. At medium speed and part throttle, still leaner mixtures must be supplied for good fuel economy. For maximum power, richer mixture is needed. Now, it's a fact that the engine uses 30 or 40 times as much air for maximum power as it does when the engine is idling. This will give you some idea of how difficult a job it is to provide the correct ratio of air to fuel for each operating condition.
Wow, I never realized the amount of air going through the carburetor changed that much.
Hey, where did you come from, Joe?
I just happened by. I thought you wouldn't mind if I listened in. There are a lot of things I don't understand about carburation.
Well, you're welcome to stick around, Joe. Before we tackle the carburetor, let's consider a couple of important facts about fuel and airflow. Scientifically speaking, both gasoline and air are classified as fluids because they can be made to move or flow. For example, water is a fluid, and it flows readily through a garden hose. Because air will flow through this air hose, it is also a fluid. But what causes fluids to flow? The flow of any fluid is the direct result of a difference in pressure. The direction of flow is always away from the point of higher pressure, toward the lower pressure area. It doesn't matter whether the pressure difference results from increasing the pressure at one end or by reducing the pressure at the other end.
In other words, you can move a fluid by increasing pressure at one end and blowing it through a tube, or you make it flow by reducing the pressure at one end. In either case, it's the pressure difference that moves the fluid. Let's see how this applies to the engine and to carburation. The engine's job is to produce power, but on the intake stroke, it's a very efficient vacuum pump. The downward movement of the piston creates a partial vacuum in the cylinder. Atmospheric pressure pushes air through the carburetor, the intake manifold, and into the low-pressure area in the cylinder.
Then vacuum is just another name for low pressure.
Right, Joe. And now let's clear up one of the most important devices used in carburation. I'm talking about the venturi. A venturi is simply an hourglass-shaped reduction in the size of a tube or passage. Since the same amount of air flows through all parts of the tube, it has to flow faster through the smallest part of the venturi. For example, if the venturi is only half as big as the rest of the tube, the air will have to go twice as fast to get through the venturi. As the velocity of the air flowing through the venturi increases, the pressure decreases, and the lowest pressure is at the narrowest point in the venturi.
Wait a minute. It seems to me that pushing more air through a narrow space would increase the pressure.
That's a common mistake, Joe. Now, do you want the fluid dynamic explanation of how increasing velocity decreases pressure, or will a garden variety example do the job?
I'll settle for the simplified explanation, Tech.
I'm sure you've used a bug sprayer, Joe, and know that pumping air across the nozzle pulls liquid out of the pickup tube. Can you tell me why?
It's because the pressure at the nozzle is lower than the atmospheric pressure on the fluid in the reservoir.
Right, Joe. And what happens when you pump faster and harder?
You pull more bug spray out of the tank. I get it. Increasing the speed of the air flowing past the pickup tube lowers the pressure at the top of the tube more, so there is an even greater pressure difference between the top and the bottom of the pickup tube. Is that all I have to know about the Venturi to understand carburation?
The fluid dynamics definition is more complex and scientific, but if Tech's explanation helps you understand what a Venturi does, we'll let it go at that. Now that we've covered some of the fundamentals, let's build a simple carburetor. A passage with a Venturi, a discharge tube, and a fuel bowl are about all we need for a constant speed and load engine. As we'll see a bit later, the level of the gasoline in the fuel bowl must be maintained at a constant level. That's what the float system does. The fuel pump takes gasoline from the tank and delivers it to the fuel bowl inlet at a constant pressure regardless of engine speed. The needle valve assembly and float control the flow of gasoline so that the level of the fuel in the bowl is always the same. The slightest drop in fuel level allows the float to drop, and this opens the needle valve. As soon as the level of the fuel in the bowl is restored, the float closes the needle valve again. Under actual operating conditions, the float lets the needle valve open just enough to meter fuel flow and maintain a very precise fuel level. It is impossible to overemphasize the importance of setting the float carefully so that correct fuel level will be maintained under all operating conditions. If the fuel level in the bowl is too low, air flowing through the Venturi will have to lift the gasoline farther. As a result, fuel flow will be reduced in proportion to airflow, and the mixture will be too lean. If the fuel level is high, too much fuel will be discharged into the airstream, and the mixture will be too rich. So correct float setting affects both performance and economy. Next, let's add the throttle valve. The throttle valve controls the amount of air-fuel mixture entering the intake manifold. It's simply an airflow control valve. Since we've covered the very basic fundamentals of carburation, let's move on to the idle system and other systems required in a practical carburetor for a car or truck. At idle, airflow is greatly reduced by the almost closed throttle valve. The space below the throttle valve is exposed to manifold vacuum, so this is a low-pressure area. The idle port is located just below the closed throttle valve. The small amount of fuel needed at idle is drawn from the idle port and mixed with the air flowing past the nearly closed throttle valve. But let's follow fuel flow from the fuel bowl to the idle port. The idle system starts at the main metering jet. From there, fuel flows upward through the idle tube. Fuel flow is limited by the idle system metering restriction, usually part of the idle tube itself. Above the idle tube, the idle passage takes a couple of turns and leads to the idle port.
With the port end of that passage lower than the fuel level, how come all the fuel isn't siphoned out of the fuel bowl?
One or more air bleeds at the upper end of the idle passage prevent any siphoning action, Joe. Equally important, tiny air bubbles enter the fuel stream through these air bleeds. This helps the fuel mix more uniformly with the air flowing through the carburetor. But that's only part of the air bleed story. Additional air is bled into the idle system fuel stream through the transfer port, located just above the closed throttle valve.
How come air bleeds in through the transfer port instead of fuel spilling out of it?
It's just another example of the pressure difference principle, Joe. For all practical purposes, there's atmospheric pressure at the transfer port, but there's manifold vacuum or low pressure at the idle port. So air flows into the transfer port, mixes with the fuel, and goes out through the idle port.
What happens at the transfer port when the throttle's opened?
That's coming up next, Joe. Will someone please turn the record so we can hear the rest of the transfer port story?
As the throttle is opened slightly, more air flows through the carburetor, but there is no increase in fuel flow through the idle port because of the idle tube metering restriction. If it weren't for the transfer port, the mixture would be much too lean, and a low-speed flat spot would result. Instead, opening the throttle slightly exposes the transfer port to manifold vacuum, and this causes fuel to flow from the transfer port as well as the idle port. So the transfer port takes care of low-speed, off-idle operation. Incidentally, correct idle speed and idle mixture adjustments are very important.
What is the dope on idle mixture adjustment, Pete?
The idle mixture adjusting screw is a metering needle valve located at the idle discharge port. Scientifically speaking, it adjusts fuel flow by changing the amount of idle port area that is exposed to manifold vacuum.
I can understand that, but what's the idle mixture setup on some of our past model 2 and 4-bell carburetors, those with only one idle mixture adjusting screw?
Those carburetors have idle mixture limiter screws, which were adjusted, flow tested, and then sealed at the factory. They limit the amount of fuel at idle. To provide for limited idle mixture adjustment and service, carburetors with idle mixture limiter screws have an adjustable air bleed. Opening this screw lets in more air to lean out the mixture. Closing it cuts down on the air to make the mixture richer. Incidentally, this type idle mixture adjusting screw has a left-hand thread. That means you turn it clockwise to make the mixture leaner and counterclockwise to make it richer, just like a conventional idle mixture screw.
So that's how it works. What's next?
The transition from the low-speed system to the high-speed system, Joe. As the throttle is opened beyond the transfer port, airflow through the venturi reduces the pressure enough to start fuel flow from the main discharge nozzle. At this point, the pressure at the main nozzle is lower than it is at the transfer and idle ports, so there is no further fuel flow from these outlets. As you probably know, many carburetors have a double venturi. With this arrangement, the main discharge nozzle extends into the secondary venturi where the pressure drop is greatest. But let's trace a typical high-speed system from fuel bowl to discharge nozzle. The main or high-speed jet meters fuel flowing from the float bowl and into the main well. The main discharge tube picks up the fuel from the main well and discharges it into the airstream. Now notice, there is an air bleed at the upper end of the main well. Holes or perforations in the wall of the main discharge tube allow air to mix with the flowing fuel. This helps break up the fuel and improve atomization, just like the idle passage air bleeds. So far, I haven't mentioned the fuel bowl vent. The fuel bowl is externally vented at idle only when the throttle is closed. At all other throttle positions, it is internally vented through a balance tube. The balance tube extends from the top of the fuel bowl to the air horn. As a result, the pressure is balanced, which simply means the pressure on the fuel in the bowl is the same as the pressure in the carburetor air horn.
Is that important?
It sure is, Joe. If a carburetor didn't have a balance tube, a dirty or restricted air cleaner would have a choke effect on airflow, and the mixture would be too rich. The balance tube automatically compensates for any restriction to airflow through the air cleaner. But I better let Pete tell the rest of the story about the high-speed system.
You mean there's more to it than the main jet discharge tube and venturi?
There sure is, Joe. In the simple high-speed system we've described so far, the main jet represents a fixed fuel flow restriction, and the venturi, a fixed air flow restriction. This results in a constant air-fuel ratio. A constant air-fuel ratio is okay for a constant speed and load application, but a fixed mixture ratio just won't do on a car or truck because both speed and load vary a great deal. For example, for maximum power, the high-speed system must provide the engine with a mixture that is about 13 parts air to 1 part gasoline. For maximum economy and minimum exhaust emissions, the mixture ratio must be about 17 parts air to 1 part gasoline, or maybe a little less. These ratios are by weight, not volume.
To change the air-fuel ratio, you must have to change either the size of the venturi or the size of the main jet.
Right, Joe. And one way to do this is to use a metering rod. If a metering rod is used, the main jet is big enough to supply the richest mixture needed for full power. Leaner mixtures are obtained by inserting a metering rod into the jet to restrict fuel flow.
And what controls the metering rod?
A common arrangement is to use a spring-loaded vacuum piston to control the metering rod. Under constant speed and load conditions, high manifold vacuum pulls the piston downward so the rod is in the jet. This provides the lean mixture needed for economy and minimum exhaust emissions. When the throttle is opened wide for acceleration or for climbing a steep grade, manifold vacuum drops and the spring pushes the vacuum piston upward. This lifts the metering rod out of the jet to allow more fuel flow and provide the richer mixture needed for full power. Some carburetors use a two-step metering rod. When the large diameter is down in the jet, the mixture is relatively lean. When the smaller diameter is in the jet, a richer power mixture is provided.
It seems to me that I've seen metering rods with 3 steps.
Could be, Joe. Some of our carburetors do have a 3-stage metering rod with a large upper diameter, a center section that is sometimes tapered, and a small diameter at the lower end. Still another way to vary the air-fuel ratio is to use a power jet. This is in addition to the main jet. The opening and closing of the power jet can be controlled by either a vacuum piston or a vacuum diaphragm. Why don't you explain the power valve and jet setup, Pete?
Okay, Tech. The power valve is connected to a spring-loaded vacuum diaphragm. When manifold vacuum is high, the power valve closes off the power jet. The only fuel supplied to the high-speed system is through the main jet. When the throttle is opened and manifold vacuum drops, the power valve is opened by the diaphragm spring. Fuel flows through both the power jet and the main jet to provide the richer mixture needed for full power. And that brings us to the accelerator pump. When the throttle is opened suddenly, airflow increases faster than fuel flow. That's because air is light and moves easily, but the heavier liquid fuel lags behind. As a result, the mixture goes lean, causing a momentary stumble. To prevent this condition, the accelerator pump provides an extra squirt of fuel. When the throttle is opened, the throttle linkage releases the pump rod, and the pump plunger is forced downward by a spring. This pushes fuel out of the accelerator pump nozzle. When the throttle is released, the accelerator pump arm lifts the pump plunger up, compressing the spring again. Upward plunger movement opens the lower check valve, and the pump well is refilled with fuel. The upper or discharge check valve closes and keeps air from entering the well on the refill stroke.
Spring actuation of the accelerator pump plunger provides an even, sustained flow of fuel. If the plunger were operated directly by the throttle linkage, the rate and the duration of fuel discharge would vary, depending on how fast the throttle was opened.
How about the choke? You haven't mentioned it.
A detailed explanation of the entire choke system is quite a story in itself, so I'll just cover the basics. When the choke valve is fully closed and the throttle valve is partly open, airflow is restricted, but manifold vacuum pulls fuel out of both the high-speed nozzle and the idle ports. This provides the extremely rich mixture needed to start a cold engine. The primary choke control is a thermostatic coil spring which closes the choke valve when it's cold and relaxes to let the choke open as the engine warms up. The choke linkage also rotates the fast idle cam into the fast idle position. This holds the throttle open wider than the curb idle position to facilitate starting and to keep the engine running smoothly while it's warming up. The choke valve design is in itself a secondary choke control. Since the valve is offset on its shaft, the air entering the carburetor tends to open the choke valve as soon as the engine starts and airflow increases. Another secondary choke control is the vacuum kick diaphragm. This important device pulls the choke open a very precise amount as soon as the engine starts. Opening the choke slightly prevents an over-rich mixture which might stall the engine.
I sure learned a lot about carburation and carburetors from you two. Be sure to let me know next time you plan a session like this.
We'll do just that, Joe. Matter of fact, about this time next month, we'll be back with another MTSC session on something useful and interesting. Don't miss it.